Hello, YouTubers. Dave out in Western Pennsylvania. In fact, this coming Monday, I will be an Associate Professor of Chemistry Emeritus with my university employer in Western Pennsylvania, USA, but I will be continuing my research. What I want to show you here is an update on some of my supercapacitor component research. So you can see right now with an electronic load, I am drawing a modest 150 milliamps with a cutoff voltage of 0.20 volts. What I have is a circuit with a commercial supercap. This supercap is rated at 2.8 volts, 100 farads. I've had good success with these. They're competitively priced. I purchased them online at Amazon. Here's one of them. If you do a search with this specification, you'll see them. And they are worthwhile. I found a couple of green label ones that I do not like and will not buy anymore. I would buy one, test it out, make sure it's okay before buying more of them. Anyway, it's in series with my electronic load device. I've uploaded many other YouTube videos describing the ZKE Tech electronic load. Model A10 will allow you to do cycles of charge-discharge. Model A20H will not. You will only be able to do single tests and auto tests. Okay, so what you can see right now is a typical profile for a supercap discharge. What concerns me, that's why I'm doing the research, is the voltage drop due to ESR. Now, I'm not talking about electron spin resonance. I'm talking about ESR resistance in electronics. And you can see it dropped from 1.90 open voltage down to 1.30. Now, that's a drop of 0.6 volts. And if you do an Ohm's law calculation, that is not very good. But once it drops to 1.30, then you can see we're getting the typical discharge curve. This one ran 8 minutes, 41 seconds. Now, the reason there's such a big voltage drop, usually with this supercap alone, I get about 0.2 volts, about 0.2 volts. But 0.6 is a little bit too much. And I get it down to a 0.1 volt, but that's for the supercapacitor alone. Now, what's in the circuit, you can see this plastic device. I'm using it for convenience purposes. And what I do is I drill holes in the top and bottom. I get these online from VWR. They're just handy, easy to get students up and running. Home researchers may like this too, but we want a reasonably close system. Now, I can put a little bit of epoxy or even Elmer's glue around the top and bottom. What I have in there is a section of graphite felt. Here's a typical one. And the commercial graphite felt is conductive enough to use in supercaps and is. And what I use as current collectors and these stainless steel clips, they work fine. I get them in Walmart in the craft section, and they come in different lengths, and I just pinch it directly onto the graphite felt. Now, the one that I'm running right now in here has not been cleaned. I would never recommend using the graphite felt directly out of the bag. It's going to have oil. Here's what they look like. Here's a section of the graphite pad. Okay? There's no problem with the very low resistance. I think I get 0.3 ohms per centimeter, but they work fine. But what we will do is thoroughly clean with 95% ethanol and dry and nickel plate. We do light nickel electroplating for about 20 minutes at a certain voltage. My student has that all in the notebook. And we will examine the graphite that's modified by scanning electron microscope. But it makes a difference. If you put too much nickel plate, you're going to lose your flexibility of the graphite felt. See, that's what the application of it, it's flexible. And we use activated carbon and other components, but nickel plating will do. And also, I'll use oxidizing agents first and try to oxidize and create some alcohol carboxyl groups on the surface. And we'll study that by scanning electron microscope 10 to 50,000 X. And what I do is I found interesting results with oxone, O-X-O-N-E, not ozone, oxone. Potassium peroxymonosulfate, disulfate, oxone. It's a registered trademark. And if I bathe this for about 24 hours and then go through the procedure of washing, cleaning with ethanol again, it does make a difference. We did upload a video on the use of oxone, but we'll be getting back into it in the fall. And we're looking at modifying the graphite and seeing the results. Now, the section I have in there right now in this plastic container, you can use plastic sleeves, but you got to make sure they're reasonably tight, because I am examining the large W, little I, SE, and that's water in salt electrolytes for supercapacitors. And what we have in there right now is a saturated solution of calcium nitrate in water at 20 degrees Celsius. 67 grams of the calcium nitrate hydrate in 50 milliliters of water. It dissolves very readily. We also have sodium nitrate, and we'll be preparing sodium perchlorate, which is incredibly soluble. It's like 17 molar at 20 degrees Celsius. But right now, that's calcium nitrate. And we immerse the pad in the calcium nitrate solution. I leave it overnight, gently blot dry, and then attach to the copper leads, contacts, and then we run this. So right now, this ran about 9 minutes. But the voltage drop, see, that's the thing. I want to minimize that voltage drop. We're losing energy that way, stored energy, with that size voltage drop. And I know already, if I nickel plate this, it will readily put a dent in that voltage drop at time zero. And that's the purpose of this type of experiment. My students can easily prepare. Home researchers can do this as well. There are some holes in the one that's in there. That's another story, but they are attached. And it's easy to get up and running. I've been working with deep eutectic solvents, but these salt in water electrolytes are fascinating. And you don't want it to evaporate, because if you have the dried salt on the graphite, you are going to get a lot of resistance. The trick is to prevent the water from evaporating. Now, normally with an aqueous-based electrolyte, what are we looking at? 1.2 volts? Maybe 1.3 volts. With some of these salt in water electrolytes, you're getting incredible potentials. 2.5, even into the 3.0 range of potential. So that's what we're working on, and even the leads have to be cleaned. But we're up and running, and of course, the container just preserves the solution. We gently blot it dry and put it in there, and now we'll start to look at really cleaning the graphite, having a protocol for cleaning, doing some oxidations, ultrasonications, things like that. And before I even put together a supercap with one of the salt and water electrolytes, I want to just see the performance of a candidate electrode. And what we will do in the supercap is actually soak a very thin layer of activated carbon felt with the electrolyte solution and sandwich it with the two graphite felt electrodes. So that's where we're at. And it's a starting point. It's an excellent introduction for undergrads getting involved in research, which I'll continue with, and home researchers that would like to do some electronics work and energy storage at home. And the students will learn a lot this way, and home researchers can produce a number of these salt and water electrolyte solutions. Just don't let it dry out, and we'll keep you posted on our research. As always, thank you for watching our uploads. Bye for now.